1.7 Precise definitions of limit. In 1.5, we get into the idea of what is a limit represents in a graphical formation. Right? In 1.6, we use the limit laws to compute limit of a function, and I sort of not formally, right, informally prove it to you a few of those limit laws by graphical approach. So in these sections, we're going to use a precise definitions of a limit to prove the limit of and functions. So the definition said that if a function is defined on some open interval containing the number a except possibly a itself. So what does that mean? And we know that if we have a functions, right, and that function is defined everywhere, including the a, then the limit of a functions is basically what a functions are evaluating at a itself, by direct substitution that we know on a polynomials and a rational because it's within the domain. But what this statement is saying is sometimes the function will be uh, defined around A when it's a open interval containing A means around A, but possibly A itself means the functions may not define at A itself. So there will be a hole, right? And then around A open interval is like, something like this if we enlarge the picture. So that's what this first part of saying. Then it said that the limit as x approaches to A of f of x is equal to L, right? When the limit of function as x approaches to A. So that's the key part. What does it mean by x approaches to A? And we said that in previously intuitively saying that when x approaches to A means the value of x is very close, very, very close to A, right? So how do we represent that in mathematics format when it's a very, very close to A? So then continue on definitions right here. If for every epsilon greater than 0, there is a number delta such that absolute value of x minus a is less than delta, then absolute value of f of x minus L is less than epsilon. So very, very close to A, when x value is very, very close to A, that's basically referring to in mathematical statements would be this part. Because absolute value of x minus A, that's basically talking about the distance between x and A. And to indicate that this is a very, very small number, so we use arbitrary number delta, which is a very, very tiny number, right? That's what delta representing in this case. So we are talking about in mathematical statements, right? When x is very, very close to A as well, the distance from A to x will be a very, very tiny number, delta. So meanings that, if I have, if this is A, right, going, and then it will reflect to the my other axis, and this is my, let's say this is my L. So when the X value is very, very close to A, then what happens? That's gonna reflect to the graph, and the graph will reflect to the value for us. So when we look at the second part of it, they say that the function value minus the limit is also very, very tiny number, which we call it epsilon. Absolute value of f of x minus L is what? Less than epsilon. So in this case, what we are looking at is this right here. If I have an x value is very close to A, and that will reflect to the functions, right? And the function will give us what? An output value. So this is my function value at a certain x that we just choose it. And then the distance between these functions and the limit, it must be what? Very, very tiny number. Another way of saying is as x approaches to A, very, very close to A, then the function value that we computed with that x value is very, very close to what the limit that we are trying to approach. Right? So that's the idea of the limits, right? Remember, The limit is what? Not exactly on that point, but when we are very, very close to that point, what is the value that we are approaching to? Is there any value approaches to it or not? So what this statement's guarantee is, okay, what this statement guarantee is, if you choose, an x value that is close to a, then it must, right? It must go to the limit. So in a sense of saying here, if this part right here is my a plus delta, the range, right? We have a very tiny, gap between a and um, this number x, right? I should say a minus delta in this case because it's on the left-hand side, right? Remember when we talk about the limit, we want to talk about approach it from the right-hand side and left-hand side. So this is a plus delta. And that will sort of give you like, according to this picture right here, you can see that that will give us, a range. And also this is going to help us to reflect, okay? This is going to help us to reflect on the y-axis also. Right? So on the y-axis, this is going to help us to reflect. If you take a look at this, here will be limit plus epsilon, right? A little bit above it. And here will be what? The limit minus epsilon on this part. So if you choose any x value between, this interval a minus delta and then a plus delta, then for sure, right, as we make it closer and closer to a, then the limit will be what? Approaching to L. So that's basically what this definition is talking about. But the difficult part that we have to use is on this definition is using the direct proof idea, because the conditions right here, if you take a look at it, is the statement is working with if and then conditions, right? That is a conditional statement. So that means we need to use this conditional part to satisfy so that I can make this conclusion. So the idea is like, how are we going to try to, prove it using this conditional statement? And that is something that new for us to, learn and then, practice it, right? There's a format of, you need to follow and write it. So to do this direct proof, I'm going to guide you through with a few numerical example to get an idea how to tweak around with it, right? And then work on it. So let's continue on the next example. Example 1, we want to consider the graph of the functions f to find a number delta such that the absolute value of, in this case, I should say that, absolute value of x minus 3, okay, not a, and f of x minus, instead of L, it will be what? 2. The limit that we're going to be using is 2. And we know that absolute, right here, we want to find out absolute value of x minus 3 is less than delta. Then absolute value of f of x minus 2 is less than 0.05. So as you can see in the diagrams, here's our limit, right? Because according to the definition, that's the limit. And we want that limit to be what? Only 0.05 away from the what? The function. So now this is our epsilon is what? 0.05. So I'm showing you with the numerical value to help you to visualize it. Now the question is, what is the delta that we need to use, right? So in this case, the delta is basically what? On the x-axis. So when we're looking for the delta, then we can take a look at on this. What is my x? In this case, my x will be what? 2.6, right? Remember, this is x minus a, right? That is the delta is the value delta is less than that. So in this case, my x is approaching to what? 3, right? A. and the numerical value we have is 2.6. So I want to find out 2.6 minus 3, what is this value is going to give me? So this is going to give me 0.4. And then the next one, when I look at it, right, 3.8 minus 3. Oh, that should be yeah, 0.04. And then that will give us what? 0.8. So as you can see, even though my epsilon values are the same, but because of the function, the functions is like we don't know what the function is, and then because of the function, its situations, the delta may not be the same, right? So in this case, like, what do we choose? So remember, the idea of the limits is what? Getting closer and closer to what? Uh, the number that we want to approach, in this case is A, is 3, right? So I have a distance from 3 to 2.6 and 3 to 3.8. And what happened, the smaller part is what? 0.4. Remember, we want to make it closer and closer. So therefore, in this kind of situation, when we have two different delta that we can get, then the delta that we need to choose is what? The minimum of these two, either minimum of 0.4 or 0.8. So in this case, the minimum will be what? 0.4, right? So that will be my answer to this question. The delta that we need going to be using, or we need to use, is what? Is 4.4, 0.4. So what this basically tells you is, sometimes depending on the functions, even though we already know what is the epsilon value that we want, your delta may not be what? Evenly spread it out from the A that we want to approach it. So in general, right, that's something that we want to put it in the notes right here. Right? In general, once we find a delta, any delta that's smaller than, that value, smaller than, will work. So as you can see right here, I got a range, right, from A minus delta to A plus delta. If I choose any X value that is smaller than the interval, right, the interval number, then it will always what approaches to L for sure, if you look at this graph, right? So that's something that you want to, like, clearly understand, right? Because when we are proving, we may run into this kind of situations. We're gonna have two different delta, and then which one will work, right? Always like you choose a smaller one, because once we find out something is works, it's always what works. So here's a notes that we want to put down, right? So the notes will be once, right, we find a specific delta for certain epsilon, then, right, then any value, right, less than that delta will also work, right, for finding out that epsilon. So that's the key things that we wanted. All right. So let's take a look at on the next example, example number 2. That doesn't have shows you graphically anymore. All right. So example 2. Let f of x be equal to x squared, and find the number delta such that f of absolute value of if absolute value of x minus 1 is less than delta when x squared minus 1, absolute value of x squared minus 1 is less than 0.5. So first of all, what you need to do is you need to understand how to look at this in the format of the definitions. So we have what? X minus a, right? Absolute value x minus a is less than delta. Then we have a functions minus the limit is less than epsilon. So in this case, it's telling you that, hey, the function value minus the limits, we want that distance, meaning like, how much it's going to be closer. That will be less than what? 0.5, right? So in order to get that, right, and how close the x value that we need to choose, right, or how close the distance between x and a, the limit that we want to approach it to, should be. So that's another way of saying is what is my delta value should be, right? The distance between x and 1, which is how close the x value that we need to choose to 1, so that what it will be, the distance will be what, smaller than the delta. So we want to find out what the delta is. Now you may see, you may think of this as like, what is the usage of this definitions other than proving these functions? Remember that the functions are, representing a different models, right? It could be in natural situations like natural sciences, businesses, right? So this is more of like a error analysis that we are talking about on our functions. Right? So let's keep it simple and then take a look at on this, right? So in this case, we have, you know, given to us is like epsilon. So how do I find out how close this delta should be? So the way that we can approach is, this is the way that we can go, right? To find out what is x. So we can use from like, inequality that we learn, we can use to find out using this absolute value of x squared minus 1 is less than 0.5. And then our goal is to find out what is the delta value. So somehow the manipulating this inequality, and then try to get what is absolute value of x minus 1 is going to be. And then we want to find out, is that even possible, right? So that I can talk about, related to the delta value, because the delta value is relating with what, this inequality, x minus a is less than delta. So in here, then I can basically start from the definitions of absolute value, which is basically bounded between these two numbers. And by adding 1, this will become 0.5 is greater than less than 1.5. And when I take the square root on both sides, it will be 0.5 is less than x and less than what, square root of 1.5. Oh, so I sort of get what the x is bounded between. Now what I want to do is what I want to get this part. So therefore, then I can start, saying that, hey, uh, if I want to, remember the distance that we want is always what? It's positive, right? Absolute value we're using it. So we can start considering, hey, what if I get like, x minus 1? So I can say that my lower bound of x, that will be square root of 0.5 minus 1. And what is the value that we get? That's approximately, if you use a calculator, 0.292. And now I want to find out what is the bound of the upper bound, right? Which is this, upper bound right here on this, meaning it's approaching from the right-hand side. So this will become, square root of 1.5 minus 1, that is approximately 0.224. And those are the two different values that we can get from like what, right? The approaching to A. And remember that from the previously, we want to always choose the smaller one of it. So my delta must be chosen from what, the minimum of 0.292 or 0.224. So therefore, the delta that we need to choose, right? This is therefore 0.224. That's approximations. And we know that, let me use the set notation. And we know that, anything, once we found out a delta, any value that smaller than this delta will also satisfy what, the conclusions that we want. So in this case is what, x squared minus 1. So what does this example basically, show us? And this example sort of like, give you a guideline or an idea of, right, the proof that we're gonna be interested in the next example. So it sort of shows you the structure. If we have right? If we have, or if we can find out or assume some particular epsilon, then we can work backward, get into the conditional part that we want to get some idea of which delta we should pick, right? So that's like sort of like cheating, right? You're working out from the answer, but that's not actual proof. That's just basically what a um, an estimation that you try to look for yourself, and then using what you found out right here to prove it in an actual proof. So I'm gonna warn you in advance that you may feel confused and then lost because the proof that we write it down, you will probably see that, hey, I just did everything like that backward earlier. The answer is exactly yes. That's the trick that we're gonna use. Okay. So from this example, I want to shows you the structure of how we're gonna tweak a little bit on the direct proof. Because when we're using the direct proof, right, we need to start from the if statement, because in a conditional statement, we need to start from the if statements, which is using the conditional part, right, to get and reach to the conclusion that we want. But without the delta, the ideal choice of the delta, we cannot start, from this conditional part. So that's the tweak of the some tweaks that we're gonna do. Okay? And we're gonna focus on the linear case, and then I will, on a test, I will ask you to prove for the linear case. But there are many other functions that we have: a quadratic, absolute value, radicals, rationals, right? Those you can study by yourself later on, if you go into lower divisions up an undergrad course, if you're going to be in a math major. If you are not in a math major, then knowing the linear proof and how this precise definition, using the precise definition to prove directly, uh, if you get an idea, that's good, right? So let's take a look at our next example. So example 3, we want to use the precise definitions to prove the following limits, right? A, limit as x approaches to 4 of 2x minus 5 is equal to 3. By this is a linear functions, and then by direct substitution, when you plug it in, this statement is a true statement. But the limit laws, come up with every single limit laws can be proved by using these precise definitions of limit. Right? So the key things that we want to know, remember, right, to prove this precise definitions of limits, then we always need to remember this part. Let me write it in pink. We are interested in showing in general, right? In the previous example, we have a numerical value, but you know that the idea of the limit is what? The number is very close and closer to um, the limit that we want to approach. So we also need to remember that, for every epsilon, there exists a delta such that, okay, such that um, absolute value of x minus a is less than delta if, right? If then statement, if then the absolute value of f of x minus limit is less than epsilon. And later on, I'm gonna write this, symbolically short. So this is like, for every, in symbolic wise, we use this, right? Epsilon, there exists, right? There exists, and such that delta, such that, right? Such that, that's how we can write it down in short and symbolic part, right? But anyway, let's move on. So from the previous example, right, we got an idea of first thing, in order to use the direct proving this conditional statement, we need to start from the conditional part, which is this inequality, and to reach, right, manipulating it to reach to what? The conclusions that we want. So, which is in this case, right, I need to know what is my delta in order to start from this statement. And from the previous example, we sort of see how we can manipulate backward to get the ideal delta. So this is a two-column proof that I want you to write it down. Okay. The first column is trying to find out the ideal choice, right, for the delta. So, and this is not proof. So now we're going to start with this part. We want to find the ideal choice of the delta. So in this case, finding suitable value for delta. Okay. This is what we want to start, finding the suitable value for the delta. So what we want to do is we want to rewrite this limit in terms of what? The definitions. So this is what we are looking for right here, right? Finding the suitable value of the delta. So we can say that, you know, for every epsilon greater than 0, if absolute value of x minus 4, right, that's the limit, is less than delta, then we know that the functions, which is 2x minus 5, minus the limit is less than epsilon. Right? Less than epsilon. So right here, what we want to, use is using this, we are looking for suitable delta, right? So we're going to be trying to use the conclusion part. That's the cheating part that I'm talking about, right? The conclusion part to find out what is the possible suitable delta that we should be using. So another way of saying is we're going to try to start working out like this. This is not a proof. This is looking the tweak part. Right? We're going to start with this, the conclusion that we want, to find out, right? To find out actually what is the suitable delta that we need to use. Okay? So meanings we want to try to work it out this way. Once again, I repeat, this is not a proof. This is a tweak part, okay? To find out the suitable delta so that we, in the actual proof, we can use that to continue. So what we do is we sort of like simplify a little bit on our inequality. It's very important that you properly use any inequality property that we learn. If we haven't learned anything yet, don't try. Okay. So now continuing this will be 2x minus 8 is less than epsilon. And then what I can do is to reach it to this point, right? X minus 4. I can see that if I factor out 2, then it will give me x minus 4. Now it's much closer. Then by the property, then we can basically what? Say the absolute value of 2 times absolute value of x minus 4 is less than epsilon. So therefore, absolute value of x minus 4 is less than epsilon divided by absolute value of 2. And guess what? We reach it to the point that we want on the left-hand side of an inequality. And the right-hand side, epsilon over epsilon divided by absolute value of 2, that should be the ideal, okay? That should be the ideal, what? The delta value. And this makes it in general because in the beginning, when we were making this tweak, we stated that the epsilon can be what? Any value that is greater than 0. And we know that epsilon representing what? Not a large number, a very, very tiny number, because we want to show that the distance will be what? Very, very close, right? The distance will be very, very small and then close. So now we found out that what is the delta should be, right? So in this case, now I found out that we should choose the delta to be equal to what? Epsilon divided by absolute value of 2 to make sure that this limit will work. Right? Because once we found a delta, this value, any value that is smaller than this epsilon divided by 2, it will also work. And then again, epsilon is what? A very tiny number, right? Arbitrarily tiny number in general. So now we are done with our cheating part, right? I keep on saying cheating, which I shouldn't, right? A smart move. Let's change that, right? We get a smart move. We did a smart move and then find out what the delta should be. So now here's the real proof come, okay? So that's why I want you to write nice and neat and 2-column approach. And when we start doing the actual proof, you will be seeing that, a lot of step we did is just going backwards, right? So that's the direct proof. So here's the proof. And the following statement that I make, write it down, it must be in there, right? So what is a known part? We know that the given, right? Epsilon is greater than 0. Right? And then we choose the delta to be what? Epsilon divided by absolute value of 2. Or you can write it down too. Remember that this is a conditional statement, right? When we are proving it, right? The theorem, the definitions are conditional statements. So we have to start from the conditional part to reach it to the goal that we want. So in an actual proof, what we need to start is we need to start from the conditional part. Right? So if absolute value of x minus 4 is less than delta, and now we want to show that this gonna reach it to the conclusions that we want, which is what? 2x minus 5, the function minus the limit, is less than epsilon. So what we need to do is we need to do a lot of manipulations in between, right? From this beginning to the end. But all the algebraic step, we sort of like know that already from there. It's going backward in most of the time, except the quadratic case that I'm going to show to you later on. So in this case, the first thing what I can do is I know that x minus 4, right? Somehow from this inequality without any epsilon, we need to have epsilon. So the only way that to get is substituting the delta value that we found and then choose it. So we're going to be substituting with absolute value of x minus 4 less than delta, with absolute value of x minus 4 is less than epsilon divided by absolute value of 2. This is still a true statement because the delta is equal to, right? That's very important. So from here, we're going to manipulate the algebraic formats, which means I'm going to multiply both sides by absolute value of 2, multiplying both sides by a positive number on both sides of the inequality doesn't change anything. Now, multiplying out according to the properties of absolute value, right? This will become absolute value of 2 times x minus 4. So therefore, this will give me absolute value of 2x minus 8 is less than epsilon. But we need to get exactly the function minus the limit. So somehow I need to rewrite it into 2x minus 5 minus 3 less than epsilon. And voila, which give us what? This is basically absolute value of 2x minus 5 minus 3, which is the function minus the limit. Therefore, now I can conclude that by precise definitions of limit, okay, limit as x approaches to 4 of 2x minus 5 is equal to 3. And that is the end of the example. So example B, limit as x approaches to negative 1.5 of the functions 9 minus 4x squared over 3 plus 2x, that is equal to 6. So it looks like a rational functions, right? So the way that we're going to start is the same as before. First, we want to, find the suitable delta, right? Find the suitable value for delta. So that basically means we want to write it down, like before, very properly with the definitions, right? Everything's included so that you can see clearly what is the statement should be. So for all epsilon greater than 0, it is important because, you are generalizing the epsilon can be what arbitrarily is any small number as long as that greater than 0. Then we have what if the absolute value of x minus the limit negative 1.5 is less than delta, then absolute value of the functions, which is 9 minus 4x squared over 3 plus 2x minus the limit, that must be less than what? Epsilon. Right? That's the definition statement. Then what we're going to do is we're going to use, the tweaking part is using, the conclusion part to find out the suitable delta. So in this case, it will be absolute value. We're going to be starting with absolute value of 9 minus 4x squared over 3 plus 2x minus 6 less than epsilon. So this will give us, when we manipulate this, I can factor it out on the numerator, which is 3 minus 2x and then 3 plus 2x over 3 plus 2x minus 6 less than epsilon. And remember why we are doing this, because we want to find out the suitable delta. So the end, I want to reach to this point, absolute value of x minus negative 1.5, that is less than delta. Right? We want to reach it to this point. So continue computing on simplifying on this part. I have what? 3 minus 2x minus 6, that is less than epsilon. So therefore, in this case, I get this negative 2x, right, minus 3 is less than epsilon. So if I factor out negative 2, and this will give me x plus 3 over 2, which is x plus 1.5, is less than what? Epsilon. So rewriting it, this will be absolute value of negative 2 times what's absolute value of x. Instead of plus 1.5, I can write it down as negative minus 1.5 to get it exactly the format that we want, right? It's less than epsilon. So therefore, now I can sort of see what is my delta should be, because absolute value of x minus a negative 1.5, that is less than epsilon divided by absolute value of negative 2. So now here's the finding part that we get. So we should choose, in this case, right, the delta to be what? Epsilon divided by absolute value of negative 2, or another way of saying it, epsilon over 2. So I like to keep it with like, these negative signs right here so that when we start doing the actual proof, then what happens is we can sort of like see all the tweak part that we don't need to rewrite it again, right? So here's the actual proof. Remember, the first column we just did is just to find out what is a suitable delta should be, right? So in actual proof, right, and giving epsilon greater than 0, right, we're gonna choose. So meaning that, like, for the following proof that we're gonna do, any epsilon value that is greater than 0, right, we will be choosing delta to be epsilon over absolute value of -2. That will always work. That's what we're gonna try. So what we want to do is we want to prove it from the conditional statement part, which is this part right here, right? So we start with absolute value of x minus a -1.5 is less than delta. And our goal is to get to what? The situations that we're looking for, 9 minus 4x squared over 3 plus 2x minus 6 is less than epsilon. Right? Function minus the limits is less than something. So we already know all the algebraic step already, right? Well, all we have to do is what? Go backward to manipulate it. In here, it will be absolute value of x plus 1.5 and less than, once again, to, starting with the inequality with only the delta. How do we change it back into epsilon? How do we get epsilon? That's where we need to substitute this delta with, the value that we find out, which is epsilon divided by absolute value of -2. And now I can just do the algebraic work by multiplying both sides by absolute value of -2, which is another way of saying is you multiply by 2. Right? I like to write it, absolute value -2 as it is so that I can continue right away. So this gives us -2 times with x plus 1.5 less than epsilon. So which is -2x minus 3 is less than epsilon. So what we have right here is we know that we need to get to the fractions. So, the way that we're going to approach it is similarly what we have done on this process, right? So first, I'm going to try to create this to get 6 first. So that means I'm going to have absolute value of, right, 3 minus 2x minus 6 less than epsilon. So notice that I'm trying to use what we already simplified. I'm going backward right here to get it. So now next thing that I'm going to do is using the fractions idea to multiply, right, top and bottom by the same number, right, the equivalent form of this 3 plus 2x and minus 6. That's the answer. So which give us, this will become 9 minus 4x squared over 3 plus 2x minus 6 is less than epsilon, and which is the functions that the conclusions that we want to get. And therefore, now I can say that by definitions of precise limits, right? So I should say that precise definitions of a limit as x approaches to -1.5 of the functions 9 minus 4x squared over 3 plus 2x, that is equal to 6, and that is the end. So limit as x approaches to 0 of x to the third power equal to 0. So let's try to find, for this type of problems, like, we're going to use the cube root idea, but not necessarily always work on the square roots and stuff, right? Because even an odd index roots are slightly different. So we're going to take a look at some simple cases. So first we want to find, finding suitable value for delta. So I want to say that for every epsilon greater than 0, right? If absolute value of x minus the limit that we approach into 0 is less than delta, then, right, we have the functions x to the third power minus the limit is less than what? Epsilon. So now using the x to the third power minus 0 is less than epsilon, that's the situation, starting with that. So we want to try to get to x minus 0 is less than delta. So for this one, if I simplify this, right, this is basically absolute value of x to the third power is less than epsilon. We know that epsilon is greater than 0, so therefore I can simply say that x to the third power is less than epsilon, which is always going to be true, right, from this step to that step. So therefore I will be able to find out the cube root of the epsilon, so it's cube root of epsilon in here. So now what I can do is, like, this is basically epsilon is a positive number. Cube root of a positive number is a positive number. So therefore, this left-hand side x by itself is the same thing as what? Absolute value of x, right? It must be what? Less than 0, also less than this square cube root of epsilon, right? Because any, and then that will help us to see that absolute value of x minus 0 is less than what? Cube root of epsilon. So we can do that. So now using the proof, right? Using this to prove it, because we know that we should choose, right, the delta to be cube root of epsilon. So in here we can choose this now, saying that given epsilon greater than 0, we choose delta to be cube root of epsilon. Okay. So starting with the condition part, x minus 0 is less than delta. So I can simply say that absolute value of x minus 0 is less than cube root of epsilon. So since this is like, a positive number, right? Epsilon is a positive number. So x value is less than what? We can think of it this way. And then raising the power 3 to both sides, which is x to the third power. And epsilon is greater than 0, so absolute value of x to the third power minus 0, that will be epsilon. So therefore, I can say that limit as x approaches to 0 of x to the third is equal to 0. So I'm talking about like very loosely right here, right? You have to be careful. So, I just want you to go and look at this appendix A, right? And that will be precisely on like, 8-7, page 7. Then you will see that this property that we use, I'm loosely using this right here. So to be more precisely written down, then I should say that, absolute value of x to the third. So this is, I said it as positive, but to be more precise, using the property, this is same equivalent, and then this is equivalent, and therefore I take the cube roots. So that's what we get. Right? Similarly, right here, for this, I can just state that and then use the absolute value of x to the third power using the property, and then this exponents go inside, right? using the property, and then this is basically what absolute value of x to the third minus 0 is less than epsilon. So I'm just like, say it out loud and then using it loosely earlier, right? Because of idea of a positive number. So this will be more proper way of writing using the properties and stuff, right? So I want you to make it more formality, right? Okay. So the last example that we want to look at is, the polynomial functions, but is a second degree quadratic. And once you get a quadratic, then you will be able to see how to manipulate on the other one as well. Okay. But it's a little bit more complicated on the manipulations part. So be ready, because this is going to be like about like a page long, right? Because of like some condition make a difference. But the idea, the structure that we're going to start is the same. So first we want to find out, right? Finding suitable value for delta. So in this case, what we're going to do is like, as before, we want to rewrite it into definition formats. So for every epsilon greater than 0, right? And if absolute value of x minus 2 is less than delta, then we know that the functions, absolute value of the function x squared minus 2 plus 2x minus 7 minus the limit is less than epsilon. So like before, we're going to start from, the absolute value of x squared plus 2x minus 7 minus 1 is less than epsilon from this case. And our goal is to get, x minus 2 is less than delta. But we will see there like, some situations, and how do we manipulate that. Okay. So working out like usual in this case, that will be x squared plus 2x minus 7 minus 1 is less than epsilon. Simplifying further, x squared plus 2x minus 8 is less than epsilon. Then the only choice we have left is factoring out, which is x minus 2 and then x plus 4 is less than epsilon. And notice that right here, using the properties of absolute value, I can say that absolute value of x minus 2 times the absolute value of x plus 4 is less than epsilon. So therefore, a lot of times, like, for this type of quadratic problem, right, on a manipulation part, the student would think that, oh, the ideal choice for the delta, we should be using epsilon divided by absolute value of x plus 4. And this is wrong, because remember that the delta is what? A arbitrarily small number, okay? A fixed arbitrarily small number. But when you say epsilon divided by x plus 4, absolute value of x plus 4, every time x changes, my delta will change. So that cannot happen, right? We have like a specific constant epsilon and looking for what a specific delta value. But we do know that once we find that delta value, anything smaller than that will work. But before that, we cannot use the variations for the delta in a proof. So that's the mistake usually that we have, right? So now the question now is like, how do we deal with this so that I can get epsilon divided by a constant, right? Which constant must be what? Something that to do with its absolute value of x plus 4. So being said that, now this is where we need to like, go in and then find out, okay? So this is like a little bit of side work that we need to deal with this. So we cannot just like write it down epsilon divided by x plus 4, right? So what we want to do in this case is we want to find out. Give me a second. Okay, to save time for the recording part, I'm sort of writing this down, right? So we got in this situation, I already pointed out that our delta we cannot represent it with what? Epsilon divided by x plus 4, right? That cannot be done because x cannot be a variable. We need a constant. So therefore, what we want to do is we want to show that there will be some value k such that absolute value of x plus 4 is less than k. So therefore, from this point, once we got that k, then we can say that this expressions on the left-hand side that we have a problem right now, right? X absolute value of x plus 4 plus times with x minus 2, absolute value of x minus 2, we can use that to what? Show that this this product is smaller than k times absolute value of x minus 2, because you already found out k that is like, upper bound for this. And at the same times, the product will be epsilon less than epsilon. So therefore, we will be able to find, a constant value for delta when we divide it by k on both sides. So in order to do that, what we need to do is we need to make assumptions, right? So the assumption part is this right here. So since we said that, we understand that if we found a delta value, right? And any delta value that's smaller than that will work. So the assumptions right now that we need to do is assuming that my delta is equal to 1. And why do you choose that delta is equal to 1? And, from what we want to point out is this, right? This assumption comment right here to find out what k value is. So in this case, what happens, I can say that x minus 2 is less than the delta, which is x minus 2 is less than what? 1. And with these assumptions, like, why do you assume that this delta is 1? Um, doesn't have to be 1. It could be any numerical value that you want, right? So far away from 2, 1 unit away from 2, in the interval left and right, that is a reasonable unit that I can use. I can use even smaller than that, which is 0.01 or 0.02, so on and so forth. But keep in mind that if we find one delta value that works, anything that smaller than that, smaller than, any x value that you choose smaller than this delta, which is within the range interval, will also work. So the purpose of choosing 1 is simply just for the computational part, for the good computation. And our goal is, remember, to find out a k value that will bound it to this absolute value of x plus 4. So by making assumption that delta is 1, I'm going to try to work it out to find out that bounds. So according to the definitions of absolute value, this is what I can get. And adding both sides by 2, this is what I will get. And what we want is what? X minus x plus 4 in this case, right? So by adding 4 to both sides, and this is what I get, right? By adding 4 to all. Oh, my bad. I made a mistake right here. That should be 3. And so therefore what? This should be 7 when I add 4. So you can see that this absolute value of x plus 4 is between 5 and 7, right? So x plus 4 is greater than 5, which is greater than 0. So therefore, I can say that absolute value of x plus 4 is what? Using the larger bound, must be less than 7. So that sort of shows us what our k value should be. So this is the larger bound to, if it is smaller bound, then you might be, some value that fishy that it will not work. So larger bound will be always working. So therefore, right, from here, we see that x minus 2, absolute value of x minus 2 times with absolute value of x plus 4, that must be smaller than absolute value of x minus 2 times with 7 for sure. Okay? So now we found out our k already. So therefore, I can continue working on this such that, right, absolute value, right, with its assumptions that we get with these conclusions, now we can say that, from continuation of absolute value of x minus 2 less than x plus 4 is less than epsilon, and we can say that what 7 times absolute value of x minus 2 is less than epsilon. So therefore, x minus 2 is less than epsilon divided by 7. So what happened now is we have assumption, we got this 7, right, by making k equal to 7 by making assumptions of delta equal to 1. And then using that to find out, my other continuing case, which is continue from here. Right? That I got another delta is epsilon divided by 2. So what will happen is, in this case, we should choose the delta for the minimum of 1 or epsilon divided by 7. So either one that we need to choose. Okay? So this is the manipulation part of it. A lot of things that I said it, but didn't write it down. So now, continuing this, on a proof of this, everything will be working backward. Right? So proof, and the I said it's going to be long because now we have what, 2 delta to choose. So given epsilon greater than 0, right? And we have what, the choice of the delta to be the minimum of either 1 or epsilon divided by 7. So we have to prove both of them it works, so that way, everything will come down. So case 1 is what, choosing the delta to be equal to 1. And that basically implies, right, when the delta is 1, that means what, 1 is a minimum. So 1 must be smaller than epsilon divided by 7. Right? And knowing this, that basically tells me, 7 must be less than epsilon. When I use multiply to both sides, because that's going to help us a lot, right? By thinking about this case in the beginning, right? When we start choosing the delta equal to 1. So working out, absolute value of x minus 2 is less than delta. And our goal is to reach to what, the quadratic case. So this is basically going to tell us absolute value of x minus 2 is less than what, 1. And that basically implies, I can multiply both sides by absolute value of x plus 4. Okay? Multiplying by positive numbers perfectly fine. Then this basically tell us this absolute value of x plus 4, right? X minus 2 is less than. And remember that this x absolute value of x plus 4 is what? Less than 7. Okay, because we found it out from here. So I can replace this by less than 7. That's still true. And then absolute value of x plus 4 is less than epsilon. Why? Because I pointed out that right here, right? When we choose delta to be 1, then 1 less than epsilon divided by 7, which is 7 is less than epsilon. So that prove it, let's prove it from this step to this step, that using this, that prove it, we have one case done, right? Something that we want. So this is basically become x plus 4 times with x minus 2 is less than epsilon. So therefore rewriting everything, x squared plus 2x minus 8 is less than epsilon. So this is basically what, x squared plus 2x minus 7 minus 1 is less than epsilon. So we got one part proof. Then the next part that we're going to have to prove is the same thing. This time we're going to be choosing the delta to be what, epsilon over 7. So again, that implies that, right, epsilon over 7 is less than 1. So we're going to have to, somewhere we're going to have to use this. Absolute value of x minus 2 is less than delta. And therefore, I can say that the delta is replaced by what? This epsilon over 7, which both sides multiply by 7 less than epsilon. Right? And now, by using it again, since the 7 is greater than x plus 4, so that basically tells me, x plus 4 times the absolute value of x minus 2 is less than 7 times absolute value of x minus 2. This imply, right, from here, this imply that x plus 4 by transitivity, absolute value x plus 4 times the absolute value x minus 2 is less than epsilon. So therefore, I will get absolute value of x plus 4 times the x minus 2 is less than epsilon, and therefore this gives us plus 2 minus 8, and then rewrite it into the function minus the limit format, and then conclude our proof. Now I can say that finally limit as x approaches to 2 of x squared plus 2x minus 7 is equal to 1. Okay? So a little bit like, it's normal that if you feel overwhelmed, right? When I was taking this one class, when I see the very first time this proof, direct proof, using definitions of limits, I don't know what the hell's going on, right? Honestly. And then I need to sit down and then start thinking about carefully each step. What are we doing? And notice that every step, it has to be logical because you are doing inequality. If the inequality is not like, logical from one step to another step, then your proof is wrong. Okay. So the key thing is, understanding like, the structure of the proof. First, we use like, the conclusion part to tweak around and find out the suitable value of delta so that I can use that to, prove it a direct proof format, which is starting from the conditional statement and then try to reach to a conclusion statement. Without knowing what delta we should use, that would be a mess. So therefore, we make a smart move by like, cheating. Okay. So try it out. And then if you have questions, please let me know.